So, the last time we were talking about sets. And so the last concept we really kind of talked about was subsets, right? So intuitively speaking, a subset is maybe a smaller set within the set that you have. Uh, um, Before I get started though, let me say something about something to be careful with when you're doing proofs. So let me ask you this right here. Compare not to assume conclusion. So let me give you kind of an example of what I mean about hazard. So suppose I want to prove this. Suppose I want to show the absolute value of x minus y is equal to the absolute value of y. Right. So suppose I want to do this. So here's what I do. I say, well, case one. So I'm gonna break this down into cases. I'm not saying this is the best way to do it, but I'm trying to illustrate the hazard here. Okay, so for x minus y be d. And since I'm in this first case, I know that d is greater than or equal to 0, right? So here's my proof. Absolute value of x minus y, absolute value of y minus x. Let's see here. That's d, right? And what's the absolute value of d? Well, since d is greater than or equal to 0, it's d. And what's the absolute value of negative d? Also d. Check. So case done. What is wrong with this? Logically speaking, the problem is I started with what I wanted to show. This is what I want my conclusion to be, right? I want to show this. I started with my conclusion and I went through a sequence of steps which were correct and came up with a true conclusion. Can somebody tell me what's logically wrong with that?
The first shown the y minus x minus d, then gone from that to that's the value minus t.
Well, given the fact that I'm in this case, there's nothing wrong with the sequence of steps. What is incorrect is to come to the conclusion that this is true. And here's what I've essentially do. If I call this statement A, and I call this statement B, then what I have shown is A implies. Now, first of all, that's the wrong implication arrow in the first place. But here's a bigger problem. When is A implies B true? It is true if B is true or if A is false. So if this had been false in the first place, the fact that you came to a true conclusion is meaningless, right? That's why that doesn't work. So for example, let me give you a silly example. This is a logical problem is if you start with a false premise, if you assume the conclusion, it turned out it was false in the first place, you're totally hosed because you know nothing about what you get from it. Let me give you something. I think we can all agree this is false. Right. Otherwise, change your major, right? This is false. Now, I bet I can derive something false from this. Watch this. I'm gonna add one to both sides. Right? No surprises there. I started with something false, I got garbage out, right? But I'm gonna prove something true from this. I'm gonna do the same thing. I'm gonna add one to both sides. Same step here. But 0 equals 1, so I can replace that 0 with 1, and I get 2 equals 2, which is true. So when you start with a false premise, you don't know the status of what you get after that. Right? And that's a problem. So be careful about that when you do your proofs. So getting back to the sets here, now that I've given you my little sort of tip for the day. How do you suppose we're going to define, what does it mean for two sets to be equal?
They contain precisely the same numbers.
Oh, yeah, that's it. So that's a good, yeah. We say the sets A and B are equal. Yeah. They have precisely the same elements. I like that. I didn't throw that in. Can somebody give me another way in terms of what we've already done to define? So I'm going to do something. This is sort of more intuitive, and it's sort of what you would want. You want the two sets to be the same. They have exactly the same elements in them. Here's another way to put this. And whenever I ask you, and it will happen in this class, are these two sets equal? Here's the way you prove it. If and only if A is contained in B, and what else? Good. They contain each other. Right? This is kind of the standard way. If I ask you, are two sets equal? This is what you want to show, that everything in A is contained in B, and everything in B is contained in A. Definition. It's interesting things. Set. But A, the set, we define the power set of A. When I see P of A, that means the power set of A. To be so. set of all subsets of the empty set. How many subsets of the empty set are there?
One.
Only the empty set itself. That's the thing. We've looked at this one before. This one has 8 elements. Let's see, it's got A, B, C, everything. And it's got all the subsets SAS 2. It's got A, B, C, and the empty set. So the power set of a set is just a collection of all subsets. Notice how the power set seems to have more elements than the set itself, right? Empty set has 0 elements and its power set has 1. ABC, that's got 3 elements in it. Its power set has 8. And we're actually going to learn a little theorem about that here in just a moment. But first I've got to give you another definition. Definition. 2.8. Let A be a set. Precisely. An element. So it's a finite set. It's not like the real numbers or the natural numbers that have infinitely many elements, but it's just got finitely many. We say that the say the I'll try to stick to the word cardinality. Sometimes you hear the word order. Of A. Cardinality based in M. When you see this kind of absolute value notation around a set, what that means is, hey, that's telling me how many elements are in that set, period. This is more sophisticated when you've got infinitely many elements. Like right now, you might be like in calculus and write the cardinality base infinity for a set that's not finite. But we're going to learn how to distinguish that even further later. Okay. Any questions on that? Okay, so now that I've told you what cardinality of the set is, here's a theorem. Let A be set with any applicants. Was it? Oh, that's a good idea, but it doesn't quite work. Yes,
It's 2 to the end, 2 to the last, sorry.
it's 2. My goodness, how are we going to prove this? I mean, oh, look, I've got 2 examples. Here we have the cardinality of the empty set is 0, right? And this is, there's 1 element, which is 2 to the 0 power. The cardinality of this is 3. And here I have 8, which is 2 cubed. But of course, this could be coincidence, right? Not a proof. How are we gonna show such a thing? Let me do a special case first, because I'm gonna do some counts. Okay, so this crazy thing works if A is the empty set. But of course, I've got a much longer road to go down, right? Because how does this work for any finite number? I'm gonna prove this actually later in the course with a different technique. But I think that if we think about it, we can figure out how to prove this now.
So second day, element days, it's either there or not there, it's choose.
That's exactly, I think that's exactly kind of the best way to go about this. Let's suppose if A is not empty, then it's got stuff in it. So I can write it down. Then cardinality A is n greater than 0. So we'll write A is equal to A1, A2, A. Now, consider all binary numbers. Where each epsilon is 0 or 1. So computer scientists are probably salivating at this point, right? But what we're doing is we're just making the strings of 0, 1, and how long is my string? Exactly as there's 1 digit for every element of the set, right? So for example, one of my digits might be 1, 1, 1 all the way up here. Another example might be 0, 0, 0, 0, 0, 0, like that. How many of them are there? Blank such binary. If n was 1, if you only had epsilon 1, how many choices do you have? It's either 0 or 1, right? So you got 2 choices. What if there's only 2? You got 4. You got 2 choices for this, 2 choices for this. They're all different. 4. How about this? 8. So how many are there? 2 to the n. Everybody agree with that? 2 choices times 2 choices times 2 choices times 2 choices. Do that n times when we get 2 to the n ways to make this. And for each such digit, corresponds uniquely to a subset of A. We will say that AI if S in A is a subset, then AI is in S if epsilon I is 1 and AI is not in S if epsilon I is 0. So this is sort of like a little clicker here that tells me for each of these elements, are you or are you not a subset? So, for example, let's make sure we got the gist of this. What if I have the binary number 1, 1, 1, 1? What if they're all ones? What subset does that correspond to? All of A, because everything's in there. What is the binary number that corresponds to the empty set? All zeros, right? Nobody's in there, right? What corresponds to the subset that contains only A1, A2, and AN? 1, 1, 0, 0, 0, 0, 1. Everybody see how that works? Quite clear on it. So there exists precisely 2 to the n subsets of A. Because every one of these digits, or every one of these binary numbers, I should say, corresponds uniquely to a subset. Okay, any questions on this? Notice, by the way, just for giggles, we give you kind of an unnamed corollary. Here. I can use one calculus on this, as a matter of fact. Proof. Can anybody describe for me? So you might think I'm having a stroke here, because I'm all of a sudden I started doing calculus. What does the function y equal to the x look like?
Starts at 1, then, no, exactly how it is.
It's sort of like, notice that 2 is bigger than 1. So it's the same basic shape as e to the x, right? It goes up to the right, right? It's just not as extreme as e to the x is. And as you point out, it goes to the point 0, 1, and it looks something like this. This is what y equals x looks like. Which one of the functions is bigger? The top one is, right? So, and you can convince yourself of that using some calculus if you like, but for all x bigger than 0, bigger than or equal to 0, 2 to the x is greater than x. So for all n and the natural number union 0, 2 to the n, which is better put it this way. The cardinality of P of A, which is 2 to the n, is bigger than n, which is cardinality of A. So the power set for a finite set is always bigger. Let me give you a little teaser first in the course. This theorem is true, even if n is infinite. So what that means is if this is an infinite set, this is a bigger infinity. We will actually prove that there are different sizes of infinity. In fact, there are an infinite number of sizes of infinity, which you might want to go home and take a rest after that. Okay. Any questions? Let A be the sets. Then A contained in B. If and only if the power set of A is contained in the power set of B. Okay. By the way, remember this is an if and only if, so I've got two things to do, right? I have to prove that if A is contained in B, then the power set of A is contained in the power set of B. Okay, so this arrow, we assume that A is contained in B and let X be in the power set of A. I want to show that this X that's in the power set of A actually looks in the power set of B. Now, this is a matter of kind of breaking down what this is all about. What does it mean for X to be an element of the power set of A? What does this really mean? It means that X is a subset of A, right? That's the definition. And what do we know about the relationship between A and B? And so if X is a subset of A and A is a subset of B, then what can we say? X is a subset of B, right? And what does that mean? Right, but in particular, it means that X is in the power set of B, because by definition, it's a subset of B. So what have we shown? We've shown that if X is in the power set of A, then X is in the power set of B. So I've got that. Started from this assumption, got it. Right, okay. How about the other way? Now we start by assuming that the power set of A is contained in the power set of B. Now suppose so this is the arrow going this way. Now we want to start with this statement and go through a logical sequence of steps and get that A is contained in B. Okay. So now we know that the power set of A is contained in the power set of B. Well, how do I show that A is contained in B? Well, somebody recall for me, what is the power set of A? Set of all subsets, right, of A. So notice One subset of A is A. So would everybody agree that A is certainly in the power set of A, which is in power set of B? Because that's what we're getting. So A is in the power set of B. And what does it mean for a set to be in the power set of B? It's a subset of B. Because this is the collection of all subsets of B. A must be one of them. Okay, any questions on this? Yes.
Question on notation. So we use like the element when it's like, when we're just talking about like it's in it and then contains if it's a set.
Right. I'm glad you asked that question, right? This means as a set, this is a set of, it's a set of sets, but it's a set. It's contained in this perhaps bigger set. And then you're confused because I wrote this, right? Because this is a set. But what are the elements of the power set? The elements of this set are sets. And this is a set that is contained here as an element, right? So for example, if I give you the set here, notice, power set of A is a collection of subsets. There's only 4 of them, so I can write this down. Now notice A is an element of A. Right. A is a subset of A. Now consider that this is the element and this is the subset, right? And notice that A is an element of the power set of A. Because there it is, right? This set, it's a set, but it's a subset of the power set because it's a collection of sets. I know does that help kind of wrap your head around it a little bit? Okay, so the next thing we're going to try to conquer is operations on sets. And I suspect that a lot of you have seen this because I know that they use this in calculus sometimes. They talk about unions and intersections when you're looking at intervals. We're going to go through this carefully. So let's let A and B be sets. I am going to define these so-called operations on the sets. Number one, the union of A and B is, how many of you have heard of the union of two sets? Like this is something that you might have encountered. This is the set X such that, and by the way, I'm assuming that my X here comes out of some master universe that I'm in that contains the sets A and B. What does it take for an element to be in the union? We're in the great union of the United States, right? You can be a Tennessean, you can be a South Carolinian, you can be a Californian, and you're part of the union, right? You might live in A or Texas B, or like former President George Bush, you might live in many states. Right. 2, the intersection of A and B to mean being the intersection. You have to be in both. Notice how this is sort of a smoother version of the or. There's your or, and this is kind of a smoother version of the and that's exactly what's going on. The difference of A and B is the set difference is should be English, shouldn't it? This is all the stuff that lives in A, but not in B. And so this is X is in A and X is not in B. And four, if A is contained in U, so this is U might be my big universe that I live in. Like for example, if you're in calculus and you're looking at the real line, that might be your universe, right? Where you're looking at intervals inside there. Then the complement of A complement of A with respect to this universe is sometimes it's written A with a superscript C. This is the set of everything in the universe such that X is not in A. So it's sort of the opposite of A, if you will. It's everything in the universe that's not in A, right? So for example, if I look, if my universe is the real numbers, right? If my universe is all the real numbers, and my set A is the rational numbers, what is the complement of this? It's every real number that is not rational, or more commonly known, the irrationals.
Okay.
Okay, let me give you kind of a warm-up proposition here. Proposition. If A is contained in the universe U, then A complement is U minus A. Okay, so I want to go, this is kind of not too difficult to prove, but I want to go through this so that we make sure that we're careful about proving set. So my claim here is this set is equal to this set. Remember, how do we show two sets are the same? I'm trying to show the two sets are equal. Show that the left side is contained in the right. Show the right side is contained in the left, and I'm good to go, right? So let's let so take an element of A complement. By definition, in fact, I left them up here so that I can look. This means X is in U, and X is not in A. Which is precisely the definition of U minus A. Because to live in U minus A, X lives in U, and X doesn't live in A. So if I'm contained in if I'm in A complement, I'm in U minus A. And the other way is going to be essentially the same. We need to be careful. I need to show this. Let Y be in U minus A. By definition, Y is in U. Let me read it here. Y is in U, and Y is not in A. Again, by definition, Y is in A complement. Okay, any questions? Okay. Let me give you a definition here. And then I'm going to do some properties of these operations. Let A and B be sets. We say A and B are disjoint. Okay, so now I'm turning into kind of a literature class here. When you hear the poetic word disjoint, what does it make you think?
Sections, no.
Yeah, that's exactly right. That's exactly right. Disjoint kind of means nothing in common, right? And so this is exactly the way we define this. There's nothing shared by A and B. Okay. A lot of. All right, I'm going to, let me apologize beforehand. I'm going to give you a boatload of properties of this. Some of these will be pretty obvious, I think. And you can probably help me write these down. Some of them will prove. Theorem. 325. Let A, B, C be sets. Following point. Number one. any set is contained in that set union something else. When you intersect two sets, it's contained in fact, I could also write B, right? A intersect A is contained in both A and B, but logically I only need to write one of them. What happens when you intersect a set with the empty set? What should you get? You should get the empty set. Because there's no elements, there can't be. What happens if you union? You get the set itself, right? When you union the set with the empty set, you get the entire set, the set A. What happens when you intersect a set with itself? It should be the set itself, right? What happens when you union the set with itself? Also A. It doesn't matter what order you intersect sets in, you get the same result. It doesn't matter what order you union sets in, you get the same result. A, take away the empty set. But you've taken away nothing. Fraction A. The empty set, take away any set is empty because there was nothing there anyway to take away from. You have associativity of unions. A union, B union C is equal to A union B union C. You also get associativity of intersections. By the way, you all should notice, I hope, looking forward in this, that this very much mirrors what we did earlier with the ands and the ors and the ands. It should look familiar, and that's not a coincidence. In particular, A intersect B union C. You might want to take a stab at this. It should be the intersection union A intersect C. And there's a similar one. It should be A union B intersect A union C. Uh, 15, so we should know. A is contained in B. And this seems kind of obvious, but this is actually useful. If A is contained in B, when you union the two, you don't get anything new. So it's just the bigger set. A is contained in B. If and only if A intersect B is A. And this is kind of a inequality sort of thing. Down to 17. If A is contained in B, then A union C is contained in B union C. And A intersect C is contained in B intersect C. We will prove some of this next time. I think a lot of these will probably be obvious, think about it, but try to absorb that. Let me know if you need any help, and I'd love to see you on Friday. They have no elements.
Oh, but the separate.
Right, they're intersections, so remember what this is this is the set of
I did,
everything
yeah.
that's contained in A and also contained in B. If they've got nothing in common, then there's nothing in that set.
Oh.
Right, sure. Mhm. Yeah, but that has to hold for everything. Right, so what it needs to be prime is if P divides A, B, then P divides A, or divides B, right? But that holds true for every pair of A, B, right? So it seems like what you're saying is P is very large.
Yeah.
Then this implication would start, this would be false, right? Because,
Yeah.
P is too large, 5, right? But this has to hold for everything, right? So even though P is large, the A, B is large enough to compare C to B.
Every combination of A and B.
Yes, that's right. Right, formally, for all A, B, Q prime. If for all A, B, integers, well, if we if P, one, and for all A, B, and integers. Five A, B, plus B, five A, plus B.
Okay,
This has to hold for all.
that makes.
Okay,